In this video, we are going to derive the time-dependent and time-independent Schrodinger wave equations. We use time-dependent Schrodinger wave equation when a particle is under the influence of a time-varying potential, because in that case, the potential energy of the particle also varies with time. For example, when an electron in an atom interacts with a photon of suitable energy, it can absorb the photon and be excited. Here, since the electron is under the influence of the time-varying potential of the photon, such cases are explained and calculated using time-dependent Schrodinger wave equation. We use time-independent Schrodinger wave equation when a particle is under the influence of a potential which is not varying with time, because in that case the potential energy of the particle also doesn't varies with time. For example, consider an electron in an atom. The electron is under the Coulombic attraction of the nucleus, which is not a time-varying potential. So here, in order to find the energy of the electron, calculations are done using time-independent Schrodinger wave equation. Before going to the derivation of time-dependent and time-independent Schrodinger wave equations, you should be familiar with these two equations for a photon, namely E is equal to h cut omega and P is equal to h cut k. In the equation E is equal to h nu, instead of nu, you put nu is equal to omega by 2 pi. Now the equation becomes E is equal to h omega by 2 pi, or it is equal to h cut omega, where h cut is equal to h by 2 pi. Again, from the expression for the Broglie wavelength, P is equal to h by lambda. Instead of lambda, you put lambda is equal to 2 pi by k, where k is the wave vector. Now the equation becomes P is equal to hk by 2 pi, or it is equal to h cut k, where h cut is h by 2 pi. In the coming essay, there are places where we have to substitute for omega as E by h cut and k as P by h cut. Derivation of time-dependent Schrodinger wave equation. Consider a particle moving in the positive x direction. Since the particle is moving, matter waves are associated with the particle, and the quantity that characterizes the de Broglie wave is given by the wave function psi as psi is equal to a into e raised to I kx minus omega t. If the particle was moving in the negative x direction, we would have written it as kx plus omega t. But here, since it is positive x direction, it is given as kx minus omega t. Let E be the total energy and P the momentum of the particle. Then, as in the case for a photon, here also we can write E is equal to h cut omega and P is equal to h cut k. In the expression for psi, that is psi is equal to a into e raised to I kx minus omega t, instead of k you put p by h cut, and instead of omega you put e by h cut. Now the equation becomes psi is equal to a into e raised to I by h cut into px minus et. Put this as equation number 1. Now you differentiate equation 1 with respect to x twice. That is, first find dou psi by dou x and then dou square psi by dou x square. In the expression for dou squared psi by dou x square, when you substitute for a into e raised to I by h cut into px minus et as psi, you will get dou squared psi by dou x square is equal to minus p squared psi by h cut square. On rearranging, we get p squared psi is equal to minus h cut square into dou squared psi by dou x square, and you put it as equation number 2. Now again take equation number 1 and differentiate with respect to t once. Then you will get dou psi by dou t is equal to minus I by h cut into E psi. On rearranging, E psi is equal to I h cut into dou psi by dou t. Put it as equation number 3. Now you must be familiar with equation 4, which you have studied in your plus 2 classes. E is equal to p squared by 2m plus v. It gives the total energy of a particle as sum of its kinetic energy and potential energy. Now multiply equation 4 throughout by psi. You will get E psi is equal to p squared psi by 2m plus v psi, and put it as equation number 5. On substituting equation 2 and equation 3 in equation 5, you will get I h cut into dou psi by dou t is equal to minus h cut square by 2m into dou squared psi by dou x square plus v psi. This is called the time-dependent Schrodinger wave equation. Please by heart this equation. When you put del square psi instead of dou square psi by dou x square, you will get the time-dependent Schrodinger wave equation in 3 dimensions. Derivation of time-independent Schrodinger wave equation. As I have said earlier, in many situations, the potential energy of a particle does not depend upon time. The forces that act upon it and hence the potential vary with the position of the particle only. That is, potential is a function of position only. As in the previous case, you write the wave function for a particle moving in the positive x direction as psi is equal to a into e raised to I by h cut into px minus et. You must have heard of separation of variables for solving differential equations in your maths classes. So using variable separable form, you write psi as psi is equal to psi 0 into e raised to minus I by h cut into et, where psi 0 is equal to a into e raised to I by h cut into px. Here we have written psi as a product of a position dependent function psi 0 and a time dependent function e raised to minus I by h cut into et. Put this as equation number 1. Please note that in the previous case of time-dependent Schrodinger wave equation, equation 1 was psi is equal to a into e raised to I by h cut into px minus et. But here it is psi is equal to psi 0 into e raised to minus I by h cut into et. Here also, as in the previous case, you differentiate equation 1 with respect to x twice. Hope you remember that in the previous case of time-dependent Schrodinger wave equation, after finding dou squared psi by dou x square, we had made some rearrangement and wrote an equation for p square psi. But here, no such rearrangement is needed. Just write the expression for dou squared psi by dou x square and put it as equation number 2. Now you again take equation 1 and differentiate with respect to t once. You will get the expression for dou psi by dou t and put it as equation number 3. Now you substitute the equations 1, 2 and 3 in the time-dependent Schrodinger wave equation. Substitute the values of psi, dou psi by dou t and dou squared psi by dou x square in the time-dependent Schrodinger wave equation. Cancelling out the common terms and on rearranging, you will get the time-independent Schrodinger wave equation as dou squared psi 0 by dou x square plus 2m by h cut square into e minus v into psi 0 is equal to 0. On putting del square psi 0 instead of dou square psi 0 by dou x square, you will get the time-independent Schrodinger wave equation in 3 dimensions. Please by heart this equation too. So in this video, we learned about time-dependent and time-independent Schrodinger wave equation.